Okay, everybody, lesson 11.2 is going to start us on a series of lessons about three-dimensional shapes. So what I want you to do first is I want you to look at the three basic shapes that we have at the top of the page here. And just like it asks you here, what are their names? You're going to be asked to do that in Edpuzzle as well. So take a minute, type in the names of those shapes. All right, so hopefully that was a piece of cake. We know this first one is called a rectangle. The middle one is a triangle. And the last one is a circle. And these are three very basic two-dimensional shapes, okay? But since our focus is going to be on three-dimensional shapes, then I want you to have an idea of where these two-dimensional shapes can play a part in some three-dimensional shapes. So when we're talking about a rectangle, with 3 dimensions, where we'll see a rectangle get used is, for example, in any sort of prism. So there's rectangular prism, there's triangular prism, there's lots of different kinds of prisms. But the rectangle definitely is involved in making a three-dimensional shape called a prism, a triangle. Hopefully this one is definitely something you can imagine. Triangle is a shape we see with a pyramid, so imagine the Luxor. Down on the strip, you see triangles that make up the sides of that building. Okay, and then the circle, the three-dimensional shape that we a lot of times think about coming from a circle is the sphere, or like a ball shape. Okay, so these are just some of the three-dimensional shapes that we're going to be dealing with in Unit 11 or Chapter 11. Today, what we want to learn about is something called platonic solids, okay, or at least these 5 here are called platonic solids. And really what we want to look at is how three-dimensional shapes have faces, vertices, and edges. Now at this point, if you don't have your vocab for 11.2 nearby, you might want to pause and grab it so that you can be referring to that as we go through and we start talking specifically about these things. By the way, these three-dimensional solids, I've included their technical names. You don't have to know those by heart. If we wanted you to know those, they'd be in your vocab, but I put them there just in case, that's something you'd be interested in. Also, if you Google platonic solids on Wikipedia, you'll see these shapes and you can animate them so you can really see all around them, not just the side we're looking at, but you can see the back, kind of where those hidden, very light colored edges are. It's kind of a cool thing, and it might help you to visualize them better. Okay, so what we're going to do first is we are going to look at faces, vertices, what we get when we add the faces and the vertices together, and edges. And in the end, we're going to be looking for a pattern between some of those numbers. So we're going to start by looking at the octahedron, which is the third figure above. Okay, now you probably recognize the prefix octa, like if you know what an octagon is. It's a polygon or a closed shape with 8 sides. An octahedron has 8 faces. Okay, faces are the polygons, or the shapes that make up the sides of these three-dimensional figures. So this octahedron is put together by faces that are triangular in shape. It's like 2 pyramids, 2 Luxors stuck together at the bottom. So if I have this square pyramid here and I had another one that I stuck on it right here, I would have in front of me an octahedron. Okay, so octahedron has 8 faces. Now it's not super easy to count on these drawings here. Like I said, if you pull these up on Google and animate them, you can see it really clear. But I can see on this front part, here's 1, 2, 3, 4 of the triangular faces. And then behind each of those, back here, I've got 4 more. So it has 8 faces. Okay. Vertices. Vertices are like the corners. These are the points where 3 or more edges meet up. So if I start looking for those corners, or where the edges which are these line segments, meet up, I've got a vertex up here. So there's 1, here's 2, 3, 4, here's 5, okay? And then I've got one more back here in the back of the figure, behind it, that's it's kind of hard to see. So there's really 6 vertices. So there's 3, 4, 5 that we can see, and then there's this one other one back here. So there's 6 vertices, or think of those as the corners. In some cases, they're sharp corners. All right, now if we add the faces and the vertices together, okay, we have 14. Okay, just the 8 plus the 6, and then the edges. So again, the edges are the line segments formed where the faces intersect. So where this triangle and this triangle intersect, there's an edge. And where this triangle and one of the ones back here intersect, there's an edge. So the edges we can see, there are 1, 2, let me do it this way. 1, 2, 3, 4, 5, 6, 7, there's 8. But then there's some in the back of this figure that we can't see. And actually, there's 4 more. There's 1 here, there's 1 here, there's 1 here, and there's 1 here. So there's a total of 12 edges. All right, now let's do the same thing with the 4th picture. Now this one, again, it's not super easy to count on these. We're just trying to establish a little bit of a pattern. So I'll count as much as I can, and then I'll describe the back side of the figure so that you have an idea of where the final numbers are coming from. Okay, so let's look at this dodecahedron. So a dodecahedron, its faces are pentagons. The faces have 5 sides. So this is a pentagon, this is, all the way around. So as far as faces go, though, again, we can get a hint. Dodeca means 12. Deca is 10, do is 2 more. So this polyhedron has 12 faces. Now we can see this one out front. So there's 1, 2, 3, 4, 5, 6. Okay, and then on the back side of this figure is the other half of it, which looks exactly like what we see out here. So 6 faces out front, 6 faces in the back. Total of 12 faces. Vertices, again, those are the corners, right? Where all those edges, those 3 or more edges come together. So vertices, I have 1, 2, 3, 4, 5. Okay, and then I can see some of these other vertices. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I can see I've got those 15 vertices. And then back here, where we can't see it as well, there are 5 more. Okay, there are 5 more. So 15. These I don't want to count a second time because the back half is joined with these guys to the front half. But then there's 5 that we haven't even counted yet in the back. So total 20. All right, faces plus vertices, 32. All right, edges. Okay, again, not an easy thing to count. If I just look at what I can count in the front, there's 5 edges right here. Okay, and then I've got this one, 6, 7, 8, 9, 10. Wait, 6, 7. Okay, hold on. I'm going to do that one more time. Here's 5. Okay, so I've got 6, 7, 8, 9, 10. And then I've got 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, that's 20 edges. And then the part back there that we can't see, there's actually 10 more. All right, so that's a total of 30. Now remember, these 2 pictures, the reason that we looked at those, I know it's hard, especially this one, to try to count all of that when you can't pick it up and move it and look on the back side. But we're just trying to establish a pattern, okay? We're going to do the same thing with some simpler 3D figures here just like it says, the more common ones, like we see here, we'll be using in class. All right. So here's what we're going to do. We're going to look at a rectangular prism. I'm going to bring one into view in just a second. We together will figure out faces, vertices. We'll fill this in. And then I'm going to show you 3 more figures and have you figure out how many of each thing there are. Okay? All right, so we're going to start with a rectangular prism. So think of like a Kleenex box, any box with a lid on it. Think of as a rectangular prism. Okay, that's a really good example to think of a box. So here I have a rectangular prism. Okay, so I'm going to kind of just turn it so you can see all the way around it. Okay, there's a rectangular prism. So let's do some counting. So faces. So I've got the top and the bottom. So there's 2 faces. And then I've got the rectangles that go all around here. So that's top and bottom 2, 3, 4, 5, 6. So I have a total of 6 faces. Okay, much easier to count on here than the octahedron and the dodecahedron. All right, vertices. Okay, remember vertices are the corners where the edges come together. So I've got these 4, 1, 2, 3, 4. And then on the bottom, I have 4 more. 1, 2, 3, 4. So I have a total of 8 vertices. Okay. Faces plus vertices, well, those add up to 14. And then the edges. All right, so I've got these 4 edges here. Okay. I've got 4 just like those 4 on the bottom. So that's 8 edges altogether. And then I've got the edges going around here. So 9, 10, 11, 12. So I have 12 edges. Okay. Now, I'm going to show you each of the next figures. We're not going to see something made out of toothpicks and gumdrops. If we were doing this in class, we might be able to do that. So I'm going to show you a square pyramid. I'm going to turn it different ways, and then you are going to stop and fill this in. And then when you've got that answered, then you'll see the triangular prism, same thing. All right, so here we go, square pyramid. All right, so there's the top of it. Okay, I'm just going to kind of turn it. Don't worry about that mark there. It doesn't mean anything to us right now. Okay, bottom. All right, so let me kind of hold it like that. Turn it like that. All right, so there was your square pyramid. All right, next is the triangular prism. Okay, so I'm going to start it here. Okay, there's the top, there's the bottom. Okay, there's the sides of it. One more time. All right, there's your triangular prism. All right, last, triangular pyramid. Okay, there's the top, there's the bottom. I'll just kind of turn it so you can see it from some different angles. All right, there was your triangular prism. Okay, let's check these really quick. I'm just going to fill these numbers in. If you got different numbers, you might want to back up in this video and go back and watch that shape again as I showed it from different angles and see if you can tell how I got the numbers that I got. All right, so here's the whole idea. We kind of went through all of these. There's a relationship we want you to see. It says, looking back at all your answers, what is the connection between the answer for F plus V? So that's this column right here, and the answer for the edges. So take a minute and write down what you think the connection is between these numbers and these numbers. And look all the way down. Look for a pattern. All right, so hopefully the connection you saw was that the number of edges was always 2 less than the number of faces plus vertices. In every single case, this number was 2 less than this number. So one way we can write that is we could say, well, the faces plus the vertices is equal to the edges plus 2. Or you might have said the faces plus the vertices minus the edges equals 2. That's another way that we could say it. All right, but that's the relationship. The faces plus the vertices is 2 more than the edges are in every single case. This is a true connection in geometry. A mathematician by the name of Euler, I'm going to write it down right now so you can see the weird spelling. This is called Euler's formula. And one of the many things he discovered in mathematics was that if you add together the faces and the vertices of a polyhedron, okay, that's going to equal the number of edges plus 2. Okay, or if we do a little algebra and subtract e from both sides, faces plus vertices minus edges will always equal 2. So you're going to want to know one, at least, version of this formula by heart. Okay. Now let's do a little bit of practice just using it. Okay, so we're going to start with this three-dimensional figure up here. It says, how many vertices, edges, and faces does the polyhedron to the right have? What is the name of this polyhedron? Okay, so let's see. Vertices, edges, faces. Okay, so let's start with vertices. We're going to do this one together so that you can then do the next one yourself. All right, so vertices are like the corners, right? So I have 1, 2, 3, 4, and then on the bottom 5, 6, 7, 8. Remember that this thing, I'm going to go over this a little bit. Okay, that extra edge in the back. All right, so we have 8 vertices, 8 corners. Okay, edges. So let's see, I've got 1, 2, 3, 4. I've got 4 just like that on the bottom, 5, 6, 7, 8. And then I've got the edges on the side, 9, 10, 11, and then the one in the back is 12. So I've got 12 edges. Faces, those are the shapes that make up the top, the bottom, and the side. So I've got the top and the bottom, which are shaded in dark on this one. So I've got those two. And then I've got the faces that make up the sides of this box. So that's these two plus this one in front, this one on the side, and this one in the back. So I've got a total of 6 faces, the top and the bottom, and the 4 around the side. Okay, now we know this is called a cube, or a hexahedron is the fancy name for it, but this is a cube. This is a box shape. Now, let's just kind of check Euler's formula to see if it holds true here. All right, so remember, faces plus vertices should equal the edges plus 2. So let's see. Faces plus vertices, so 6 plus 8 equals 12 plus 2. 14 equals 14. Okay, that works out. Okay, we can see that it makes sense with that figure. So now you're going to try this one. Do the same thing. Figure out how many vertices, edges, and faces this polyhedron has, and then verify Euler's formula once you have figured out those numbers and see if it works. If you've counted these up correctly, this should work. All right, so let's see what you guys got. So you should have, here, I'm just going to put this page up here. So you should have 8 faces, the top, the bottom, and the 6 rectangles that make up the side. You should have 12 vertices. You have 6 corners up here and 6 corners down at the bottom, and 18 edges. You've got 6 around the top, 6 around the bottom, and then 6 around the sides. And then when I checked it with Euler's formula, I did 8 plus 12 faces plus vertices. This time I did the minus 18. Okay, I just did faces plus vertices minus edges, which is supposed to equal 2. And that gave me 20 minus 18, which is 2. Okay, you can check it the way that we did the one above 2. You can go faces plus vertices equals edges. Sorry, let me just put the number in there. Equals 18 plus 2. This is 20. This is 20. That works. All right. Now we have kind of a weird question next. If I took this prism, this is called a hexagonal prism, by the way, because the top and the bottom of it are hexagons. If I were to take that and cut it open and lay it flat so it looks two-dimensional like this, the question is, do you think the formula would still hold true? Would the faces that we see plus the vertices that we think we see equal the edges plus 2? Okay, so what do you think? All right, so let's test it out. Okay, let's test it out. So faces, well, those are the shapes we see. So we've got these 2 hexagons and then 6 rectangles. So I have 8 faces, or sorry, yes, I have 8 faces. Okay, now the vertices and the edges, let's see, well, with vertices, we're used to just counting corners. So if we count the corners of all the shapes we see, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So if I count them as corners or where line segments are meeting up, there would be 22. Okay. Now, we know that vertices are where 3 or more edges meet. So if we go by definition, the way that this is laid out, the only vertices we really and truly see are these 2 and these 2. But that doesn't match, neither of those numbers match what we got when the shape was in its 3D form. Okay, and then for edges, okay, up here, remember we got 18 edges. If I count edges I see here, so I've got 6 edges on this hexagon and 6 on this one, so that's 12. And then I have 13, 14, 15, 16, 17, 18, 19. And then I've got these 5 here and these 5 here. That's a total of 29 edges. Very different from what we got up here where we only had 18 edges. So this definitely, if we look at, if we go 8 plus 22, okay, equals 29 plus 2. Well, this is 30 and this is 31. Those aren't equal. So it definitely doesn't hold true when you pull apart the figure and make it two-dimensional. Okay, it's got to be in 3 dimensions. It's got to be put together in order for this to hold true. Okay, last thing. I want you to try this last question. Using Euler's formula, how many vertices does a polyhedron have if it has 15 faces and 39 edges? Okay, so grab your formula and see if you can figure this out. All right, So let's take a look. So I have 15 faces. So I'm going to put 15 in for F. I'm asked how many vertices, so I'm just going to use a V there. Keep that the same. Edges, there's 39 plus 2. So we have to solve for V. So this is just algebra. I'm going to add 39 and 2. It's 41. So 15 plus V equals 41. Subtract 15. So we get 26 vertices. Okay, so I don't have, if I know 2 of these 3 things, I don't have to have the shape in front of me. I can use this formula and figure out how many of the missing thing that I have. So hopefully you got that one right. And at this point, you are ready to work on your Alex homework for 11.2. I'll see you guys when we come back after the second online day on Tuesday. Have a good rest of your long weekend.